Hello everyone, good morning and welcome again to our online science class. Today is the first day of the week, so hope that you are pumped up with energy for our topic for today. We'll have a very exciting topic and very technological topic for this week. So if you have your course book, your pen and notes with you, we're going to start with our topic for today. It's all about magnetism and we're going to focus here about electromagnets. So if you have your course book with you, kindly open it on pages 168 and 171. You're gonna take a look there about making an electromagnet on 30.4 and 30.5 is stronger electromagnet. These two topics are really related with each other, so we're gonna take them as one. And today we're gonna learn of the following. We're gonna analyze here the parts of an electromagnet, and you can see there the train and how it is related to the machines made by the train, but not that train. This is a different kind of train. I'm gonna show it to you later. So we're gonna determine also the factors that makes a strong electromagnet, and we're going to investigate the magnetic field of an electromagnet. So first, since we're talking about an electromagnet in here, I want you to take a look with this one. It's a picture right over there. So what can you see? You can actually see there a loudspeaker. And to make a loudspeaker, we need one important material that we're going to put in here. And what is that? That is a coil around a metal or any magnetized metal, and that's the reason why it is moving right over there. So a material can be magnetized that produce movement just like this one, and when it produces a movement, the air vibrates and therefore we can hear the sound, and that's technically how the loudspeaker functions. So it moves like a motor, and in that case a motor is found inside a loudspeaker. So as we go along, we're going to take a look there what helps the loudspeaker to move and what mechanism does it uses to move. So I want you to look again at this picture. So you can see there's a metal and there's a coil. It's bronze in color. So the metal is the one where we're pointed by the pencil. So will you consider this as a magnet? What do you think? Well, can you see a north pole and south pole in it? Well, definitely we can't see any poles in it, but can we consider that as a magnet? Well, we can consider that as a magnet, and what are the evidences that we can see that is a magnet? First is that the metal seems to be floating on the magnetic field of the coil. So we call the wounded up bronze thing here as a coil, and therefore we call this one as an electromagnet. Well, we have there two words which will help you define what is an electromagnet. We have there the word electro, and of course that refers to electricity, and we have there also the word magnet. And the word magnet, I think you're really familiar with that those are any kind of materials that attract other metals or other magnetic materials. So let's take a look more about what is an electromagnet. So you can see here a magnet and an iron filings, and we did this kind of experiment last time using a simulation, and you can also see this one. So how is an electromagnet, this one, is different from an ordinary permanent magnet? Well, to differentiate these two, we need to take a look first at the characteristics of these two materials here. So what is happening here in a magnet in iron filings, that the iron filings are just attracted to the magnet because of its magnetic force. But I want you to take a look with the electromagnet here. So we can turn it on and we can turn it off. After that, this metal clicks or attracted to it. So what we need here is that we need a power source. So this one are connected to the power source. And we also need there a coil. So the coil there is made up by a wire. So it needs a wire wrapped around a metal, or sometimes we don't need a metal. So we need a metal there to make the electromagnet stronger actually. And the magnetic force can be switched on and off. And this is just the difference between these two. So again, both of them acts like a magnet. However, the materials are really different from the two. So this can be made up of a magnetized object, and it becomes a permanent magnet. However, this one is just made of coil which is wound up with each other. You need a power source and it becomes a magnet, and therefore we call that as an electromagnet. So let's take a look with the device that is found there. Again, it is an electromagnet. So we have there the switch which tells it to turn on and off, and that's the time when it's going to behave as a magnet. And we have there the coil. It's pretty obvious right over there. In this case, it's wound up in a metal, and of course it has a power source which is not just shown in here. It becomes a magnet when this one is turned on. So what is an electromagnet? What do you think? So an electromagnet is otherwise known as a second type of magnet, or it is otherwise known as a temporary magnet, because you just need a coil there and you just made it if you connect it with a power source. So an electromagnet is a magnet that is made up of a coil wire which produces a magnetic field. So to analyze how does the electromagnet behave, let's take a look with this one. So this is now my power source. This one is the switch on, switch off of that, and I coil the wire here in an iron nail, and I have now here an electromagnet. So if I put the compass near to our setup, look at what will happen. So to analyze this one, we need to recall, where does the blue point? Exactly, the blue always points to the north, and the red one always points to the south. So what does this mean? This means that your electromagnet now has its own magnetic field. So I want you to recall last time's activity. There's where the earth is a very big bar of magnet, and the compass moves south or north depending on where is it in the part or in the pole of the magnet. So the same thing with what's happening in here. Therefore, this is now a magnet. We had created a magnet out of just the coil, the iron nail, and the power source. And that's the reason why we call this electromagnet, because we need an electric field in here to create a magnetic field. So the compass moves because of the magnetic field, which is produced now by the coil after using a power source here. So we created a magnetic field because the electrical current is connected to the coil that we have here, and that electric current comes from the battery. So electricity and magnets, electricity coming from the electric current through the battery or any power source, which creates now a magnetic field, and hence we call this material now as an electromagnet. So the compass there, the movement of the compass proves that we had created a magnetic field. So if this compass wouldn't move, therefore there's no magnetic field. So because the compass moves, it's an evidence that we had successfully created a magnetic field using electricity. Hence, we call it electromagnet. Alright? So let's take a look with the poles of the electromagnet. So again, if it's a magnet, there should always be a pole. So this part of the battery is this one. It's the minus side of the magnet, and this one is the plus side. This one and this one is the minus side. Okay, so the flow of the electricity is from the plus side. So this one is the inward influx of the electricity, and this one is the outward flux, or the outward motion of the electricity, or the outward flow of the electricity. So this time we're going to locate where is the north pole and the south pole of our electromagnet. So based here in the diagram, which do you think is the north pole? Clue is that take a closer look at this one, at the compass. So look at the flow of the electricity and look also at where the compass is pointing. So if the blue is pointing over there, is it the south pole or the north pole? So it's pointing towards the negative. So the negative is now our North Pole, and the South Pole is the positive side here. So the flow of electricity is from here going in here, which makes this one now as our South Pole, and as it exits here, this now becomes our North Pole. So this one always points to the south, and the blue one always points to the north, and this compass would prove to us that the flow of our electromagnetic field, or our magnetic field in our electromagnet, is always from the in, which is our North Pole, our South Pole, I mean, and the out, which now becomes the South Pole. The in of the current is our South Pole, and the out of our current now becomes our North Pole. So just to look at it really easily and to visualize it easily, here's how it looks like now. So the red pointer is our south, and the blue pointer is our north. So electricity enters from here in the plus side and exits here in the minus side. So that plus side now is the south, is the red pointer, so this is now the South Pole, and this one now becomes the North Pole. So if we make a diagram on how it looks like, this is now how the coil would look like. So the in here of the electricity is from the South Pole, from here, and the out of that is to the North Pole, so this one. So if you recall how our magnet, the magnetic field in our bar magnet last time, the magnet which makes up the earth, and also a regular magnet found in the laboratory, and we put iron filings in it, it creates a magnetic field. And the same thing with the electromagnet. This is now the field of our electromagnet. So this field here shows that the electrical current creates now a magnetic field. And where is the flow of the electrical current? It creates now the North Pole and the South Pole. So the inward flux of the electrical current creates the South Pole, and the outward flow of that creates now the North Pole. So the magnetic field lines comes out of the one end of the electromagnet. This is now the North Pole, and the field line goes round and back into the other end of the electromagnet, and we call this now as the South Pole. So again, I want you to take a closer look at where is the South Pole and where is the North Pole of our electromagnet. And again, the flow of the electric current will determine where is the North Pole and where is the South Pole. And later on, we're going to connect what is the essence of knowing where's the South Pole and where's the North Pole of the electromagnet that we have, and where are we going to use that. So usually in under Faraday's law, we remember this hand rule that we have. So the thumb will always point to the North Pole of the electromagnet. Opposite the palm is the South Pole. So this one is the North Pole, and this one is the South Pole. So the flow of the current here is in a clockwise direction. So if it's in a clockwise direction, this one is the North Pole, and this one is in the South Pole. However, if we do the other way around, so it's the anti-clockwise movement of the electric current. So this one now becomes your North Pole, and this one now becomes your South Pole. So it's very easy to understand where is the flow of the current and where is the North Pole and the South Pole. So always remember, just do the hand rule. The palm will be the direction of the current, the thumb is the North Pole, and the opposite of that, of course, is the South. So if the flow of the current is going this way, so all you need to do is to flip your hand just like this one, and you would locate where is the North Pole and the South Pole. Alright, so just need to remember this hand rule. So electromagnet was actually developed by Faraday way back before, and he identified that this electric current is related to the poles which is made by the electromagnets that we have. So he also experimented when is the electromagnets going to be stronger. So I have there 4 kinds of coil. This one is the only 50 coil, this one is only 100 coil, and this one is only 150, and this one is 200. So we will be identifying, using this experiment, which of these four will be creating a stronger electromagnet. So we would be using here an ammeter to determine the strength of our electrical current. So we are going to decrease the number of coils. Here it's 4, here it's 2, and let's see. Look at that. So you can also see the light sparks from the for the light bulb here when we have 4, then when we have 2. So if we relate this one to what we have in here, which coil will have a stronger electromagnet? Is it the 50, 100, 150, or 200? Well, definitely that is the 200. Why it's the 200? Because the longer is the path of the electric current here, which speaks about the path here on the coil, the stronger the electromagnet would be. Well, how about for the number of power source that we have here? So number 1, we only have a 1.5 volts of that battery. For number 2, we have two 1.5 volts of battery. So which of the two here do you think would produce a stronger electromagnet? Is it number 1 or number 2? Okay, definitely it's the number 2 electromagnet with the 2 batteries. Why is that so? Because of course, the more source of electricity, the more electric current there would be. Well, the stronger electromagnet or the stronger magnetic field we are going to produce out of that. So I want you to take a look in here, and it's a very powerful and it's very useful device that we used a while ago in an experiment. So what is this one? We call this one as your ammeter. And what does an ammeter do? The ammeter is used to measure the current flowing through the coil, and the unit is called amps or 8. So it will tell you how strong the electric current is or not. And in the laboratory, we usually use that to measure the electric current, let's say using batteries. So, and of course, using the electric current produced by an electromagnet. Okay, so last time, a while ago, I was telling you about the uses of the electromagnet. So let's take a look with this one.
Along a 12-mile test track in Emsland, Germany. Here and in Japan, maglev engineers are developing frictionless rail systems that propel trains at speeds up to 275 miles per hour. Wondering how you levitate one of these 60-ton rail cars? The bottom section of the train wraps around a T-shaped track called the guideway. A set of electromagnets lines both sides of the train's undercarriage. An electromagnetic field generated in the guideway attracts the magnets, lifting the train less than half an inch above the track. A second set of magnets lining the train's side exerts a lateral force, keeping the vehicle properly aligned. If you're looking for the motor that propels the maglev forward, don't bother looking anywhere on the train. It's laid out flat along the guideway. A system of magnets, like that used on Magic Mountain's Superman roller coaster.
This is, for example, another application of the linear synchronous motor. If you synchronize the changing of the poles with the motion of the train, you can keep the forces going.
Train engineers aren't the only ones getting a lift out of magnetic levitation. Scientists at NASA are exploring how magnets can give the spacecraft of tomorrow a boost into orbit.
One of the
Well, that is just one use of electromagnets in our technology right now, and that gives us a very sophisticated and a very advanced way of traveling and transportation. And it produces less or no carbon dioxide at all, so it's actually very healthy for our environment. So the simplest form of how we can use an electromagnet is through this, and this is the loudspeaker. So let's take a look with it.
To produce sound, it is necessary to set molecules of air in motion. This animation represents a loudspeaker. It is an electromagnetic transducer that transforms an electrical signal into a mechanical signal. It is made up of a flexible membrane in direct contact with the medium of propagation, a conducting wire coil, a permanent magnet that encircles the coil,
So we call this now as your
a rigid container
electromagnet.
that holds everything together. Note, because it is important, that the flexible membrane is connected to the electrical coil, which is able to move freely along the length of its axis. The principle behind the functioning of this device rests on magnetic forces, to which the coil is subjected when a current is flowing through it. Let's look now at the physical chain of events. The coil vibrates at the rhythm of the electrical signal, carrying the flexible membrane along with it. The membrane transmits the mechanical vibration to the molecules of air around it, and the wave is propagated successively to nearby neighbors, like a wave in water, at a speed that is approximately 1,000 kilometers per hour.
Alright, so we have there now one of the uses of the two of the uses actually of the electromagnets, and we have a lot of them. Okay, so I just want you to click on the links right over there and you can view it on your own time. So I just shown to you these two, and these two are the simple and the most advanced use of the electromagnets in our daily life. So those are the nature of your electromagnets. So are you now ready for a very short quiz? Well, let's test how much you've learned so far. So we have here 5 questions, and then let's identify if you can answer them. Alright, so here's question number 1. Which letter here in our electromagnet setup represents the North Pole? Is it A or B? Let's check your answer. Of course, that is letter A. How about which of the two there represents the South Pole? Definitely you are correct. It's the letter B. Here's question number 3. Name this device. Correct spelling is needed in here. Let's take a look. It's the ammeter. Question number 4. Which is the strongest of the 4 electromagnets in here? The 50, 100, 150, or 200? You're absolutely correct. It is the 200. And this is the last question. Which electromagnet is the strongest or stronger between the two? Is it number 1 or number 2? Of course, that is number 2, okay? Number 2, because number 2 has more power source, therefore it has more electrical current. It carries more electrical current than that of the number 1. Alright, so how much marks did you get? Did you get all 5 correctly? If you all get them 5, congratulations. You are really, really good at magnets. However, if you get 1 or 2 out of this, you can replay this video again, and you can revise it in your own pace or in your own convenient time. So that will be all. You can scan this QR code to link on our survey form and answer there questions there about our online Google form. So if you don't have any other questions, that will be all for today. See you on Tuesday. Goodbye, everyone.